Hello JNM, this is me, Austin Fernandez, and I'm here to talk about, I can't get this marker open, okay, I'm here to talk about, damn it, there we go, I just bit it, here to talk about cache memory. Now, a bunch of you are having a slight difficulty with this lesson, so I'm here to clear this up. This is going to be a rather long video, so make sure you have some time. So basically, in the von Neumann architecture, let me get my hand in the proper place here. You have three main components. You have the input-output, you have your CPU, and then you have your memory. And these are connected by buses: address bus, data bus, and control bus. Now we're gonna mostly ignore I/O. We're just gonna focus on how CPU talks to the memory, and that's done by saying, okay, address bus, I need data from, let's say, address A403, assuming you have 16-bit architecture, which is rather small. So this translates to, if you know, binary 000000011. That address is then accessed into the memory. So let's say that corresponds to this. And whatever there, let's say we have F5, is transferred, so does the address bus. Whatever is there is transferred via data bus back to the CPU. So this is the CPU, F5, and that's stored in your CPU. Now in your CPU, that's called the memory address register and the memory data register, but that's not important for this lesson. Just know that the CPU tells the memory, okay, this is the address where I want the data, give it to me, and it stores it there. Sometimes that's a read operation. Sometimes it's a write operation, so it says this is the address where I want you to put this data. Instead of going this way, you're going to go that way. So you're just going to write to A403 data F5. Now there is some time delay between this. It's not instant, and that's called the memory access time. And usually, well, here's the thing. Main memory, the RAM of your computer, it uses dynamic RAM, which means it just has to refresh a lot. Since it does change a lot, so it has to refresh a lot. It uses capacitors, which means it's very slow. However, if you have a CPU and then you have your main memory, which uses DRAM, some architectures or organizations put in a static RAM, which uses flip-flops, called a cache, to get data, store it so that the CPU can access it faster, because SRAM is faster. It uses flip-flops. Flip-flops, basically you just feed data through. If you remember flip-flops from your digital design class, the value is just waiting to be accessed, which is what registers use in CPU. So it's very fast. However, if you remember from your digital design class, flip-flops are extremely expensive, so that's why they don't just use SRAM for your entire memory. They just use it for cache. In fact, cache only takes about 1% of the main memory. So if you have, like I said earlier, 16-bit architecture, that's 2 to the 16 bytes of memory. Usually you'd only have 2 to the 9th bytes of cache. or if this is, well, this is 64 KB, you'd only have around 512 bytes of cache. So anyway, what does cache do? Well, cache basically stores commonly used memory, and it does it by blocks, not by words. So for the purposes of this tutorial, words is not, well, x86 architecture, a word is 16 bits, but for now I'm just going to say a word is a memory location. So A403 points to a word. This is a word. This is a word. Whatever's there is a word. That's a word. Alright? A block is simply a collection of words. So let's draw a bigger cache. Let's give it 4 blocks. And here's memory. So each block in memory is actually just a couple of words, so this could be further subdivided. And why is that? Well, there's this term called locality of reference, which follows the 80-20 rule, which just says, well, if I access this memory location right here, what are the chances that I would access a memory location near it? Well, 80%. 20% I access somewhere else. But if I access that, what's the chances that I would access somewhere near it? Like, let's say here, or let's say here. Well, that's 80%, because, well, memory is usually allocated contiguously, so it's more efficient to transfer data by blocks instead of individually. So that's how cache works. So let's get down to it. Okay. Am I missing any terms? Anyway. So let's say this entire block is loaded here. So let's call this block 0001. And it's loaded here. Note that the address is not stored. I'm just saying this has the same data as 0001. This is now called a cache line. It's a line of data that is the same as your main memory. So, now what can we do here? There are two main concepts that we have to discuss. There's a cache hit and a cache miss. A cache hit is when you want to read or write to the cache and it hits, which means the address is currently on the cache. Cache miss is the opposite. The address is not on the cache. So, let's go with cache miss first. When you're reading, there are two things you can do. You can load through or non-load through. When you write, you just write to the memory. So what's the difference between load through and non-load through? Well, load through, as the name says, is, okay, so let's say this CPU. You want to access this. Let's call this FF05. But of course it's not on the cache. So that's a cache miss. In load through, you're going to of course load it to the cache. But you're going to load through the cache directly to the CPU. So you're going to load through it. A non-load through is, well, you don't load through the cache. You load to the cache, then you load from the cache. So you basically have to wait twice in the non-load through. So again, load through, you load to the cache, then you load ahead of the cache. Non-load through, you load to the cache, then you load from the cache. So there you go. Now, with a cache hit, reading is no problem. Writing is the problem. There's a write through and a write back. So with a write, let me draw another. With a write through, you write to your cache and then you write to your main memory. With a write back, you write to your cache, but you don't write to your memory. You just wait there If there's nothing being done, no memory operations, then you write to the main memory. So it's during idle time. Or when this cache location is about to be, this cache line is about to be overwritten by another cache line, you then update the main memory just to make sure that data is the same. For example, I say load 0005, write 0005. If I were to do a write through, write FA, I'd say FA, then FA. If I were to say load 00A503, I would say, okay, let's say 00A5 is here. I say, okay, 03 is here, but this still contains whatever it contained before. Now, when there's nothing being done in the memory, only then will it write there. But let's say I want to write 00AF 50F. This will, well, let's say it might be replaced. Just before it gets replaced, it writes 03, and then 0AF takes over. So that's the difference between write through and write back. Now, let's talk about cache replacement algorithms. There are three main ones: MRU, LRU, and random. Random means, well, replace randomly, so I won't really discuss that. It's pretty self-explanatory. LRU is basically the least recently used one. You replace that. So let's say you want to access 0, 2, 4, 6, 2, 8, 10, 12. And you have 4 spaces in your cache. You go 0, 2, 4, 6. You access 2. But, oh, you need to access 8. Which do you replace? Well, you replace 0. Then you need to access 10. Which do you replace? Well, you can't replace 2. You touched it recently. So, which one is the oldest? You just touched 8. You just touched 2. Well, you can replace 4. Then 12, you replace 6. Now for MRU, you just replace the most recently used one. So in this case, 0, 2, 4, 6, 2, 8, 10, 12. So now let's go to cache mapping. How are addresses or blocks loaded? Well, cache mapping, there are 3. Direct means the address tells you where to map it. Full associative means that any block can go anywhere. And block set associative means the address tells you which set to put it, but it can go anywhere inside that set, which I'll demonstrate in a while. Now direct, you have 3 fields: a tag, a block, and a word. The word tells you how many bits are used to represent a word. So let's say you have a 1 MB main memory, which will give you around 8 KB of cache. And then you have, let's say you have 256 bytes per block. So 8 KB is 2 to the 13th bytes divided by 2 to the 8th bytes per block. That gives you 2 to the 5th blocks. Now this 8 is the number of bytes used to represent the word, so you have 8 bytes here. Now the number of blocks is put in block. Whatever remains, so 8 plus 5 is 13, you have 20, this is 2 to the 20th, you have 20 bits to represent address. Whatever remains, that's your tag. So 8 plus 5 is 13, 20 minus 13, 7 bits for tag. So if you have a cache 0 to 31 and you want to place in the value A403B, this would translate to 101000000000111011. You just divide it like this. So 8, 4, 8, 5, and there will be 7 left. Whatever is here, that's where it goes. So in this case, it's at 0. So you place A403B here. You load the 256 bytes starting at this address, well, this address, assume all this 0, into that block in the cache. Now let's say you want to load FF0FF. That would translate to this, which is 16. So we have a block 16 here. That takes FF0FF. Now, if I were to take 0E012, that would be, let's make this F, I miscalculated. That would give you another 16. But there's already something in 16, so what do? Well, you erase this, and then you load this entire block. So that's 0F012. So that's direct associative, direct mapping rather. Now full associative, you just randomly place that shit anywhere. So same scheme. If I were to load A403B, I'd just say A403B. FFOFF would look like that. That could be block 1. 0F012. That would be there. And really, it's kind of trivial. There are only 2 fields here, tag and word. Word is the same. It's 8. Whatever remains is the tag. And really, it's not like this in real life. It'd be random. But the cache controller, which checks for the cache if the memory addresses are there, we'll have to check the tag one by one, and it's really slow, but it saves a lot of memory. Saves a lot of space, because here you notice I only introduced 3 addresses, and it had to kick one out, even though there were many blocks left. Here they just sat down and settled in. Now block set associative, you need to have another parameter, how many blocks in a set. So let's say that's a 4-way block set associative, which means 4 blocks per set. You would now divide this by 2 squared, because 2 squared is 4. So you have 2 to the 3rd sets, or 8 sets. Eight sets, each having 4 blocks. Something like that. So here you have tag, set, word. Word is the same. Set is now the number of sets, so that's 3. And whatever remains is the tag. So in this case, let's take this. It's 3 now. So you go to set 0 and you place A403B wherever you want. You go here, still set 0. You go FFOFF. Here, set 0, FFOFF. If we were to introduce something like 11111, Sorry. This time we need to go 3. This is the tag. This is the set. And that is set 1. So you go here to set 1. And you can go anywhere in these 4 blocks. So I put 1, 1, 1, 1, 1 there. Now in the next video I will do a sample problem that I will solve. So stay tuned.